Section 6 is called Exponential Functions. We've been working with exponents this entire chapter, and the word exponent is sitting right here in exponential. So exponential functions are functions that have exponents in them, but they're special exponents. They're not like x squared. They're 2 to the x power. So the exponent is actually the variable. That's the thing that's going to be changing, not the base. That's what makes these exponential functions. So if you see the variable in the exponent, you're dealing with an exponential function. We want to see what the graph of an exponential function looks like. So in order to find out what the graph of an exponential function looks like, we need to set up a table. So I'm going to go x and y. And then my usual numbers that I pick are like -2, -1, 0, 1, 2. Maybe -3, maybe +3, but for sure those numbers. We want to figure out what these numbers are going to be. So let's start down here first, because those are going to be easier to work with probably. If I plug 2 in for x, then what I have is 2 squared, which is 4. And I tell you what, let's go ahead and put that 3 on there. If I plug 3 in for x, what do I get? 2 to the third power is 8. Okay, I plug 1 in for x, and what do I get? Just 2. 2 to the first power is 2. If I plug in 0 for x, what do I get? I get 1, because anything to the 0 power is 1. Now what if I plug in -1 for x? It's a fraction. What is it? Yeah, it's 1/2. It's 1 over 2 to the first, which is 1/2. And if I plug -2 in, what do I get? 1/4 is correct. All right, let's plot those dots and see what we see. We have -2 and 1/4, maybe there. -1, 1/2, so like there. And then 0, 1, that's easy. 1, 2, kind of easy. 2, 4, it's right there. And then 3, 8. There's 7, so 8's going to be off my grid a little bit. Okay, so we can kind of see what's happening from -2 and then to the right. This thing's kind of taking off and doing this. But the question is, what's going to happen as we continue this way? Is this thing going to drop down here? Is it going to turn and go like that? Is it going to turn around and come up, like we've seen some graphs do? What's going to happen? Yeah, that's what happens. So let's see what that looks like on the graph. I want to take this farther. I'm going to make another table here. And instead of stopping at -2, I'm going to start at -3 and continue. -4, -5, -6. That pretty much takes me out to the edge of my graph. So what would 2 to the -3rd power be? Yeah, it's 1/8. And what do I get when I plug in -4 for x? 1/16, because it's 1 over 2 to the 4th, which is 16. So 1 over 16. And what happens, getting into some big numbers here, what happens when I plug in -5? Yeah, 1/32. So actually, is that a big number or a small number? That's really small. And how about -6? What do we get? 1/64. That's going to be tricky to graph 1/64, because basically what you're saying is we've taken this distance right here from 0 to 1 and divided it into 64 parts. I don't even have 64 pixels on this screen between 0 and 1. So it's going to be really difficult for me to draw that. But we're going to do the best we can. Is it on 0? Is it on the other side? Is it down here? No. Is it ever going to be down here? Because no matter what, if I plug in an even more negative number, like I picked -100, is that going to turn it negative? No. It's just going to make it a really, really small number. Okay, so we got to graph these. We have -3, 1/8, so like there, and then maybe there, And then I'm getting really close to the x-axis, but I'm not actually on the x-axis. There I am. So like you said, we're just getting closer and closer to 0, but we're never actually going to touch 0. Because there's never going to be a number that I can make so negative that I wind up getting 0 right here. I'm always going to wind up with a fraction. Even though it's super small, it's never actually 0. So when I draw on this graph, I need to be very careful and make sure that I'm not negative and I'm not actually touching the x-axis. But as soon as I start to go, then this thing takes off and it's easy to graph. That's what the graph of an exponential function always looks like. Kind of like a hockey stick. If you've ever seen a hockey stick, it kind of looks like that. That's pretty much what every exponential graph looks like. I could do some things to this. I could do some things to this to make it go steeper, like the 2 to the x one kind of looks like that. But later on, we'll see another one called 3 to the x power, and that one just takes off faster. Or like 5 to the x power would be like, really fast. Or I could do some things to this function and make it be upside down. So then it would look like that. Or I could do something to this function and make it look like this. So now I could also take this function and make it look like that. But they all look the same. They all have this sort of shape to them. If I turn this hockey stick around, that's that guy. If I flip this hockey stick upside down, that's that guy. If I turn it around and then flip it upside down, that's that guy. All 4 of these are what your graphs are going to look like here in this section. And that's basically what this chart right here is telling you. It says for an exponential function, it's a function of the form y equals a times b to the x. And then they say a can't equal 0, because if you just have 0 sitting here, then 0 times something is just 0, and then what's the point? There's no point in that. So a is not 0, and b has to be greater than 0. b can't be 0 either, but it's going to be positive. Okay? Now, this is what we just graphed, but y equals negative 2 to the x makes it look like this. If I reverse this, y equals 1/2 to the x makes it do this. And then if I make it negative, y equals negative 1/2 to the x, it makes it do that. So all 4 of those are there. Basically what's going to happen is, if your number sitting here is bigger than 1, you're going to get a graph that goes in this direction. Or if it's a negative, it's going to go in this direction. But it'll start off near the x-axis and then move away from the x-axis. If you have a number that's between 0 and 1, then you're going to start off way far away from the x-axis or way far away from the x-axis and then move to the x-axis. So that's kind of a pattern that you can remember that will help you with these graphs. Especially if I gave you a multiple choice question. Multiple choice question, I show you all 4 of these graphs and I give you this equation. Which one is the answer? Which graph does it most look like? Which color? Red or blue? We got that negative sign hanging out front. Yeah, it's going to be the blue one. So it's definitely, with that fraction, going to go towards the x-axis as you go from left to right. But with that negative sign, it's going to start on the negative side of the x-axis and then go to it. Process of elimination is nice. Okay, all exponential functions look like this guy right here. Y equals a times b to the x power. And when I do this, I'm going to have 2 numbers sitting here. I'm not going to be able to multiply those 2 numbers together. Do not multiply a times b first. Order of operations says exponents before multiplication. So you have to do exponents before you multiply. Okay, when we were learning how to tell if a function was linear from a table, you got to think way back, this is a long time ago, When we were learning how to tell if a function was linear from a table, what did we do? If I gave you a table and I said, is this linear, what did we look for? The change, yeah. How much does x change each time? And then we said, how much does y change each time? And if we change the same amount in x and the same amount of y each time, then we had a linear function. We were checking change in y divided by the change in x. Basically, we're calculating the slope. When we're trying to decide if a function is exponential, the table needs to have a common difference for x. So we have to change the same amount each time here. We're adding 1, adding 1, adding 1. But a common ratio for y, which means we need to multiply by the same amount each time. From here to here, we're multiplying by 3. From here to here, we're multiplying by 3. From here to here, we're multiplying by 3. That makes this an exponential function. So is y equals 3x an exponential function? What do you think? An exponential function has the x variable in the exponent. Is the x variable in the exponent here? No. X is not in the exponent. Does the table or rule represent a linear or exponential function? So let's take a look at A. First of all, our change in x is adding 1 each time, so that's good. What about the change in y? What are we doing each time? We're what? Yeah, we're adding 2 each time. Plus 2, plus 2, plus 2. So is that an exponential function? If we're adding 2 in y each time. No, it's not. What is it, actually? We're changing the same amount each time here. We're adding. Same amount each time here. We're adding. So that's linear. What about B? Is that linear or exponential? That one's exponential. How come you know? Yeah, the x is in the variable. Or the x is in the exponent. So on problems like this, and there are problems like this in the homework, 8 through 13, which you can now do, they ask you, is it linear or exponential, and then tell me why. So because I know the exponent is here, I know that it's exponential. Over here, because I'm adding by 2 each time here, I know it's linear. Up here, I know this is linear because it has the equation y equals mx plus b. It's in slope-intercept form. The x is not in the exponent. So watch out for that explanation when it says explain.